want to thank Dwayne Daniels for pointing out Greg McCarty to me. Greg is the one that's going to be doing our presentation today. He's a soil scientist with the ARS Hydrology Remote Sensing Laboratory in Beltsville, Maryland. And Greg, I'm going to turn the presentation over to you.
Okay. Thank you. So today I'm going to talk about use of principal components and scaling up topographic prediction models. I'm sorry, I'm just, okay. There we go. Okay, first I'd like to recognize our long-term collaboration with NRCS. We've been a partner with NRCS in the Conservation Effects Assessment Project, and I've been working with Lisa Duranchek and Bill Efland in the SEEP program, and they provided generous support for this work. This work originally started trying to answer very practical questions. The original goal was to develop denitrification potential maps for coastal plain landscape in Maryland for assessing the biogeochemistry of product converted croplands. So some questions that came up in my mind during that work was how best to extrapolate data to a larger setting, what type of topographic model is best for doing that, and also how to set the spatial extent of valid extrapolation. Is there an objective test to determine topographic domain? In Maryland, we had some field scale sampling done to look at prior converted croplands and looking at their denitrification potential. So we had 3 fields in Maryland, which we did the sampling. And then we wanted to be able to extrapolate that to the larger setting, to some watersheds, so we can look at, use some watershed models to look at denitrification in the watershed. But we only had access to a limited number of fields, so we were unable to test scaling up strategies from fields to watershed. In Iowa, I had some data where we had sampled both at field scale and also at watershed scale. So with the Iowa data, we could test different approaches for looking at for being able to scale up our topographic models. So that's why I went to Iowa to do some tests, and then we also used that approach in Maryland. When we talk about the modeling, of course, it's important to talk about the domains, modeling domains, and to limit, which may limit the ability to extrapolate models. An obvious one is land use and land management. In our case, we were looking at croplands only, but there's also vegetation, there's geology, there's climate, there's time domains, and in this talk, I want to focus on topographic domains. So the working hypothesis is that similar landscape processes and mechanisms will occur in similar landscapes. What is the extent of aerial extent? What is the aerial extent that a model can be scaled? Can we objectively test for landscape similarity? So the outcomes were development of approaches for defining topographic domains, and also to develop topographic models that are tuned to the topographic domain of interest. This work is highly dependent on use of LiDAR, which is a rapidly developing technology. Most of the LiDAR that is available today was collected using these small, sorry about that, so small planes that are flown at low altitude, whereas the up-and-coming technologies will allow much higher throughput gain of LiDAR data. So LiDAR data quality and quantity is likely to increase rapidly in the coming years. This shows you an example of why LiDAR data is important. This is a carbon map developed using hyperspectral imagery. I will not go into how we did that, but it shows projection of the map on two different DEM products. One is the National Elevation Database, which just shows the field being a flat, tilted plane, whereas the LiDAR has a rich amount of information on topography and reflects the relationships with carbon distribution in the field. So now I want to get into some key concepts, looking at a framework for understanding landscapes, and the framework is self-organizing networks. Self-organizing networks really caught fire in the 1990s, and the ecologists have been using them ever since to explain complex relationships within systems. So landscapes are self-organizing networks. The key requirement for those type of networks are the non-equilibrium systems. In other words, there's energy flowing through the system. In the case of landscapes, it's both in terms of water, as water flows through this landscape, and also, sun providing energy for photosynthesis. Networks are made up of nodes and links. Various nodal links allow flow of mass and energy within a landscape. Complexity develops from the complex interaction between nodes of the network via links. Structure and complexity spontaneously emerge from chaos. Once a critical number of links become established, among nodes, disorder transforms into order. This is really a rapid transition that occurs. It's referred to as a phase transition. So in other words, it's similar to crystallization. The network becomes crystallized once you reach that critical level of links. And there's an interesting publication at home in the universe that describes how this may have resulted in the origins of simple life 3-some billion years ago. In the language of networks, living organisms are closed autocatalytic sets. So the hypothesis, various covariances and correlations found within landscape topography characterize the links between nodes. Characterizing this information will capturing this information will help characterize important landscape processes and interactions. Why are covariances important? Parameters such as slope in isolation have no landscape context and provides limited information. In contrast, covariance of slope with, for example, curvature in upslope contributing area provides rich landscape context. Knowing that covariance allows us to make connections between different landscape positions. That is the network links. So many data mining approaches have been developed to relate topographic parameters to soil properties, but these relationships may not be robust. Little has been done to study the underlying landscape network and its inherent links. Topography is an important determinant of network links. And landscape parameters characterizing topography can help quantify and characterize nodal links. A young landscape, such as one formed after glacial melt, for example in Iowa, would have weak set of nodal links and resulting in chaotic landscape processes. With time, a set of nodal links strengthens, phase transition occurs to orderly landscape processes. Further landscape maturation would involve shifts in the nodal links without substantial disorder in processes. The concept is that landscape covariance will evolve with age of landscape. So landscape similarity. Similar landscapes should contain similar links between the nodes in the network. If landscapes are similar, a common model may be able to capture important interactions. We'll discuss how to objectively measure similarity of landscapes, which can then indicate applicability models across the region. So our program in study is to develop methods for studying landscape topography. That is the network links. To develop approaches for testing landscape network similarity, topographic domains, and to develop models that use information from landscape networks to predict soil properties. So how to characterize landscape topography. Various parameter algorithms can extract information from digital elevation models. There are generally three types of topographic parameter: local topographic, those that contain local attributes, and those that contain non-local attributes, and those that have combined attributes, which often imply some type of physics, such as moving water through the landscape. Use of a combination of these parameter types is important for describing landscapes. They provide a rich landscape context. So this is a listing of the local parameters that we measured in our DEMS, slope, aspect, and various forms of curvature. This is a listing of non-local attributes, including flow accumulation, positive openness, and various types of measurements of catchment. And then these are some of the combined attributes. So in all, we had 15 attributes. Now, relief is important attribute, and the question is at what scale should we be measuring relief? For example, tillage erosion may be, the important scale may be the Catena or the field scale, whereas with water erosion, it may be catchment and watershed scales. To address this, we actually measured the relief at 7 different scales, and later on I'll discuss how we handled that in our landscape characterization. This just shows you that there's a very poor correlation between small scale and large scale relief measurements. Now I'd like to introduce the concept of orthogonal eigenvectors. Eigen in German just means proper. And to do that, I'd like to talk about a physical system, in this case, an asteroid that we want to rotate. Now, if you do apply a random force to the asteroid, likely you'll get a random tumbling motion. There are exactly 3 axes on which you can rotate that asteroid and get a uniform rotation. To find the first one, you go from the center of mass, and then you look for the vector that maximizes the moment of inertia, and that will become your first eigenvector. Then you go to the plane that's perpendicular to that vector, and you look for a vector that maximizes the moment of inertia within that plane. That becomes your second eigenvector, and then the third, of course, is defined by those other 2. So now if you rotate along those vectors, you get a uniform non-chaotic rotation. The eigenvalue is the length of each of the eigenvectors. So eigenvectors and their eigenvalues are inherent properties of this object. Now, my question is, do landscapes also harbor inherent eigenvectors and eigenvalues? So we have the 15 topographic parameters that we can extract from our DEM, and then we can look at the we can analyze the variance that's in the 15-dimension covariance space that's formed by those parameters. First, we determine the eigenvector that accounts for the largest amount of variance, and we'll call that PC1. And then we look at the we search for orthogonal eigenvectors that have varying amounts of variance, and we can rank those by the amount of variance that they account for. So this is the principal component analysis. Eigenvectors are characterized by their relationship with the underlying landscape parameters, commonly called parameter loadings, or the loadings of the eigenvector. Loadings for a principal component can encode inherent landscape parameter relationships. In other words, relationships between local and non-local parameters. And eigenvalues can be evaluated for parameter values at each landscape position to create a map of eigenvalues. So parameter loadings can be used to evaluate how similar principal components are for different landforms. In other words, tests for landscape similarity. Are samples being collected in a representative landform, and is sampling properly stratified across the landscape variance? So those are a couple of questions that you can readily address by looking at the principal components. So first, quantifying landscape relationships using topographic metrics. Okay, so the area of interest we're going to be first looking at is Walnut Creek Watershed in Iowa. In that watershed, we picked 360 random points, and then we extracted values for the 15 parameters that were associated with those points. We also had soil measurements performed at both field and watershed scale. So we had 330 samples at field scale and 100 samples at watershed scale. Those soil samples were analyzed for soil carbon, for cesium-137, which is a tracer that we can use for looking at soil redistribution since about 1964. And then we also modeled soil erosion based upon the cesium data. So this is the study area in Iowa, this Walnut Creek, and the objective was to scale up soil property prediction models from field to watershed scale. So these. So first we performed principal component analysis on the 360 random samples. We ran into the problem that raw relief metric caused principal component instability when relief measurement the scale was changed. And of course that was due to the fact that the scales of relief are not highly correlated. So the solution was that we developed synthetic relief parameters by performing principal component on the relief parameter itself. So we looked at 7 different distances of relief. And then what we got out of that is we got 2 principal components that account for over 90% of the variance. And so one of the principal components is for long-range relief, and the other was for short-range relief. This indicated that these were 2 important scales there were two important scales of relief in this landscape. And so we use those 2 principal components as in our further analysis. So this just shows you the loadings associated with the different landscape parameters associated with the first 5 principal components. The first 5 principal components account for 80% of total variance in the covariance space. As you see, the loadings indicate the contribution that each parameter contributes to the principal component. It can either be a positive or a negative relationship. So then we can look at each principal component individually and look at what are the major variables that contribute to the principal component, and then we can assign some attribute to that principal component. For example, PC1 seems to be related to water distribution within the landscape. PC2 is associated with runoff velocity or acceleration. As at the bottom, you can see the eigenvalue maps associated with each of these principal components. PC3 again seems to be associated with some type of runoff parameter or process. PC4 may be related to flow acceleration. And PC5 associated with flow convergence or divergence. So my grand conjecture is that the principal components loading values encode important covariances within landscapes. Principal components can capture information on important relationships, i.e. the nodal links between different landscape positions. And principal components can be developed for the larger setting, which then can be used to develop topographic models that are tuned to the larger setting. So first, we developed some models based upon our field data, our field scale data, which is at sites 1 and 2. And we developed topographically based models to investigate the spatial distribution of soil organic carbon, cesium, and soil redistribution that was calculated from the cesium data. We used 2 approaches. One is the typical stepwise ordinary least squared regression, where we use the independent or the raw topographic parameters in our model. In the others, we use stepwise principal component analysis, where we use the principal components that were developed from the watershed to model the distributions in the field, at the field scale. So this shows you the results of this analysis, or this model development. As you can see, they actually both perform pretty well at the field scale. But if you note the number of parameters in the principal component model is significantly less than that in the ordinary regression model, which may be important in terms of minimizing the potential for overfitting data to the model. Okay, so now we have the models that were developed from field scale, so we're going to see how they work at the watershed scale. So we have our validation data at the watershed scale, so we can look at how these field scale calibrated models work at a larger setting. So we're comparing the principal component model with the ordinary least square regression model. And see the principal component models perform better than the ordinary least square model. I think what I interpret this as indicating that the principal component models are better tuned to the watershed scale, and that maybe the ordinary least square regression model was overfitting the data during calibration to some extent. Okay, so then we can take those results and we can actually create maps of soil carbon and soil redistribution at the watershed scale. And then our goal eventually is to use these the maps in watershed models to estimate the impacts of soil redistribution on carbon dynamics at the watershed scale. The lower figure, it just shows you some transects that were collected in the watershed and how our predicted model correlates or relates to actual measurements, which are indicated by the size of the circle. So now we're on to testing for landscape similarity, or topographic domains. So that in this, I'm going to use Iowa data and also our Maryland data. So these are the two watersheds of interest. We got the Walnut Creek watershed, where we had the 360 sampling locations and also 100 soil sampling locations. In Tuckahoe and Greensboro in Maryland, for those watersheds, we had 500 random sampling locations for each of the watersheds. So for each of those points, we extracted topographic parameters, and then we do our principal component analysis on those topographic parameters. So we have so what we did, we subsampled those populations, those random populations. So we created 20 subsamples for each watershed, and then we did DC principal component analysis on each of the subsample sets, and so we create a 20 subsample loadings for statistical testing. And then later we did cluster analysis to provide another test of landscape similarity. So this just shows the correlation between the loadings in the different different principal components. You see in Greensboro and Tuckahoe watersheds, all principal components were highly correlated and statistically significantly the same. Whereas when we compare Maryland to the Iowa watersheds, the first two principal components were not correlated, whereas the principal component 3, 4, and 5 were correlated. So this just shows you a table of the loadings for the different principal components and comparison of the average loading for Iowa and for Maryland based upon the population of 20 principal component runs. So this just shows plots of the loadings for principal component 1 and principal component 2 for Iowa versus the Maryland watersheds. As you can see, the Maryland watersheds are closely clustered together, and they are very distinct from the Iowa watershed. So this indicates that the Iowa watershed is different than the Maryland watershed, and that if you were to develop a model in Iowa, in all likelihood, you should not try to apply it to a Maryland watershed. But even between Greensboro and Tuckahoe, there is significant clustering, indicating that these watersheds are different in themselves. And what is known about those two watersheds is that Tuckahoe is more well drained than the Greensboro watershed, and so that may be indicative of why we get separation between these and the loadings for the principal components. Now, if we look at slope between principal component 1 and principal component 2, we don't get good separation between Iowa and Maryland. And also, if you look at the wetness index, there's not as good a separation. But if we look at principal component 3 and 4 for these same parameters, then we see good separation both between Maryland and Iowa, and also between Greensboro and Tuckahoe. So this is indicative of that these landscapes are different. Iowa more so than between the Maryland watersheds. This is an example of actually this slide is there's supposed to be another set of panels, and it didn't show up here showing the cluster analysis. But what the cluster analysis showed was that there was no difference between these three groups of points, whereas there was a significant difference between this group of points and these two groups of points. Unfortunately, it didn't show up. The panel didn't come through properly on the slide. So, conclusion. We demonstrated the utility of principal component analysis for scaling up topographic models. Models appear to be better tuned at the larger setting using this approach, and there's a reduced concern about overfitting because you've reduced the dimensionality of the model. And we also demonstrated a novel approach for testing for landscape similarity. So now we can define the topographic domain for prediction models. And this may also lead to a new way of classifying landscape topographies. So I leave you with this fun thought for the day.
All right, well, thanks, Greg, and I'll remind people that to submit a question, you put that in the Q&A pod, and that'll show up for us, and we'll be able to take that question. In the meantime, when people online compose their thoughts about a question, is there anyone here in the room with me that has a question for our presenter? So, Greg, I'll ask a question. You talked about in your write-up that this technology holds promise for useful large-scale maps of soil properties that we can routinely develop from topographic models. So what would you say the limit of the scale is? How large a scale?
Well, I think that's where our landscape similarity comes into play. And also, we need to keep in mind the other domains that I talked about, vegetation, climate, and age of landscape and things like that. And so, we can at least at this point address one of those domains, which is the domain of topography. But again, I wouldn't want to develop a model in cropland and then apply it to a riparian system or whatever. I think that would be a disastrous way to go. But as long as you keep within your domains, I think you can pretty safely develop useful models.
A lot of our soil survey map units, they're not necessarily mapping land use. In other words, we can have the same map unit in cropland as in a forested area, as in an urban park, perhaps.
Yeah.
So any thoughts about that? I mean, I know you want to stay with cropland in this example.
Well, the thing is, cropland has been greatly influenced or altered by erosion, whether it's tillage erosion or water erosion, and so it's a unique landscape, and it's not what it was originally before agriculture was introduced on the landscape, and so I think it greatly alters the properties within that landscape, soil properties within that landscape.
Also, I was surprised to hear about the development of the LiDAR coverage. My exposure to LiDAR has been as very narrow strips, but this much wider swath with the Geiger LiDAR, that sounded very promising.
Yeah, there's a couple of, there's the Geiger LiDAR, and then there's also what they call single photon LiDAR, and I think these were developed primarily in military applications, but now that technology is being released to civilian uses also. So I think this will revolutionize how LiDAR is collected. Essentially, you get a order of magnitude increase in the amount of coverage you can get per effort. So I think LiDAR will be much better in quality and also in spatial extent.
All right, Greg. Well, having no, oh, here comes some. Question is, have these techniques been applied compared with mountainous topography? Or have you just done it or know about it for cropland areas?
No, we've just done it in croplands for Iowa and Maryland.
All right. Well, having no other questions, I want to thank you, Greg, for your time and effort to make this presentation today. And thanks to all the participants for joining in. We had more than 120 people join today's webinar. The on-demand recording of this webinar will be available on our National Soil Survey Center YouTube channel within a few days. So feel free to let your colleagues know about this training opportunity. This concludes our webinar presentation.